Hello dear friends, നമ്മൾ ഇന്ന് കാണുന്നത് ഇലക്ട്രോഡൈനാമിക്സ് ബിഫോർ മാക്സ്വെൽ എന്ന് പറയുന്ന സെക്ഷനിലെ മാക്സ്വെല്ലിന് മുമ്പുണ്ടായിരുന്ന കുറച്ച് പ്രധാനപ്പെട്ട ലോസിനെ കുറിച്ചാണ്. കഴിഞ്ഞ ക്ലാസ്സിൽ നമ്മൾ എനർജി സ്റ്റോർഡ് ഇൻ മാഗ്നറ്റിക് ഫീൽഡ് എന്താണെന്ന് കണ്ടു. ഇനി ഈ ക്ലാസ്സിൽ കാണുന്നത് മാക്സ്വെല്ലിന് മുമ്പുണ്ടായിരുന്ന കുറച്ച് പ്രധാനപ്പെട്ട ലോസാണ്. അതിൽ ആദ്യത്തെ ലോ ആണ് ഗോസസ് ലോ എന്ന് പറയുന്നത്. ഗോസസ് ലോ നമ്മൾ ഓൾറെഡി പഠിച്ചതാണ്. ഗോസസ് ലോ സ്റ്റേറ്റ്സ് ദാറ്റ് total flux through a closed surface is equal to 1 by epsilon 0 times charge enclosed within that surface. അതായിരുന്നു ഗോസസ് ലോ ആയിട്ട് നമ്മൾ പഠിച്ചിട്ടുള്ളത്. ഇറ്റ്സ് ഓൾസോ റിട്ടൺ ആസ് സിൻസ് phi is equal to surface integral E dot ds, we can write surface integral E dot ds is equal to q enclosed by epsilon 0. Okay, here we can consider a closed surface. This is a closed surface. Q enclosed is the total charge within that closed surface. Okay, now we have to write the differential form of this Gauss's law. For that, we are considering a small volume inside this closed surface. Okay, let the volume element is d tau and rho is the charge density. Okay, then we can write dq is equal to rho d tau because rho is the volume charge density. That means charge by volume. Okay, here here I wrote d tau dt instead of d tau. Okay. Here we can see that q is equal to rho into v, that is charge density into volume. This is the same sense we have written this above equation. Dq is a small charge within this volume element. Rho is the volume charge density, d tau is the volume of that small volume element. Okay, now what is the total charge enclosed, or what is q enclosed? Total charge within enclosed within that closed surface. This will be equal to integral dq over the volume v. Okay, so you can write integral over v, instead of dq put rho d tau. Okay, so we have substituted dq from this and you will get volume integral rho d tau. Substitute this in above equation, in this equation, then you can write surface integral E dot ds, which is the left hand side, which is equal to 1 by epsilon 0 volume integral rho d tau. Okay, now you can take epsilon 0 into that integral because it's a constant and it will not make any difference. So integral volume integral rho by epsilon 0 d tau. Okay, in the LHS it is integration over the surface and on the RHS it is integration over the volume. So we can use Gauss's divergence theorem to the LHS. Divergence theorem on LHS of above equation. Okay, according to Gauss's divergence theorem, surface integral A dot ds is equal to volume integral del dot A d tau. Okay, this is the expression for this is the divergence theorem. Okay, just use this. Okay, so use this divergence theorem here. So instead of surface integral E dot ds, we can write volume integral del dot E d tau, just as the above equation. Substitute this and you will get it is equal to volume integral rho by epsilon 0 d tau. Okay, when you compare these two parts, LHS and RHS, is the volume integral on both sides and d tau is on both sides, then we can find that the term del dot E must be equal to rho by epsilon 0. So this is from this above equation, on comparing we can write del dot E is equal to rho by epsilon 0. Okay, this is the differential form of Gauss's law. Okay, so this is the differential form of Gauss's law in electrostatics, especially in electrostatics. Okay, in the same sense, there is differential form of Gauss's law also is there in the case of magnetostatics also, the magnetism. Okay, in the case of a magnetic material, if you are considering a magnet, if you break that magnet, a magnet is having two poles, right? Suppose this is a rectangular magnet, this is north pole and this is south pole. If you break this here, you will get a small magnet, two magnets. If you break a magnet, you will get two magnets like this, each of them having both north and south poles. Okay, so that means that if you break a magnet, you can't separate a north pole alone or a south pole alone. That means magnetic monopoles does not exist. There is a very important concept is there. Magnetic monopoles does not exist. If you break a magnet, you will still get both north and south poles. Okay, you can separate a north pole alone or a south pole alone. You will get them combined. Okay, so if you break it a very small piece, even then you can see both poles in a single piece. Okay, so that shows that magnetic monopoles does not exist. Mathematically, it can be represented by the relation del dot B equal to 0. Del dot B is equal to 0. This is also known as Gauss's law in magnetism. Okay, this relation can be derived by using Biot-Savart's law also. Okay, you can derive this relation using Biot-Savart's del dot B is equal to 0, which means that magnetic monopoles does not exist, and that is referred as Gauss's law in magnetism. Okay, now the third one is Faraday's law of electromagnetic induction, differential form of Faraday's law. You can refer that class in the above links. And according to Faraday's law of electromagnetic induction, del cross E is equal to minus dou B by dou T. Del cross E is equal to minus dou B by dou T. This is the differential form of Faraday's law of electromagnetic induction. Okay, and the next one is that Ambience Circuital Law. Ambience law. Okay, according to Ambience law, which relates the magnetic field with the current flowing through a conductor. Okay, suppose when I is the current flowing through a conductor, then integral B dot dl is equal to mu 0 I, that is referred as Ambience law. Okay, you can see that. Ambience Circuital Law. Okay, Ambience Circuital Law states that the line integral of magnetic field along a closed path line integral of magnetic field along a closed path is equal to mu 0 times net current enclosed by the path. Mu 0 times net current enclosed by the path. This is referred as Ambier's law. Okay. This law, this can be written like this. I is the current enclosed within the surface. Then we can write J, I in terms of J. J is the surface current density, that is I by area. Okay. So, I is equal to surface current density into area, or you can write surface integral J dot ds. If we are considering ds is a small area and the total current through that path is equal to surface integral J dot ds. Substitute that in above equation, then closed line integral B dot dl is equal to mu 0 times surface integral J dot ds. Okay. So, on equating or take mu 0 into the bracket, then surface integral mu 0 J dot ds will be on the right hand side, and left hand side this line integral B dot dl. Okay. Now, apply Stokes theorem on the left hand side. Stokes theorem on LHS. Then according to Stokes theorem, line integral A dot dl is equal to surface integral del cross A dot ds. Okay. So, in the same sense, line integral B dot dl will be equal to surface integral del cross B dot ds. So, the above equation will be like this: surface integral del cross B dot ds is equal to surface integral mu 0 J dot ds. On comparing, this is the integration is over s, and these parts are identical, then you can equate them, then you will get del cross B is equal to mu 0 J. Okay. This is the differential form of Ambier's law. So, these four equations, that is for differential equation, del dot E is equal to rho by epsilon 0, del dot B equal to 0, del cross E is equal to minus dou B by dou T, and del cross B is equal to mu 0 J. These are the four relevant relations that was there before Maxwell's. Relevant electromagnetic relations before Maxwell. Here two equations are divergence equations and two equations are curl equations. Equation 1 and 2, del dot E and del dot B. Here both are divergent equation, and del cross E and del cross B are curl equations. Okay, these are the Maxwell's, these are the equations that is relevant in the case of electromagnetism just before Maxwell. Okay, thank you.